Hello! In this video, we are going to prove that the two definitions of a Cauchy sequence are equivalent. So really, we're given a sequence of real numbers, and the first definition tells us for every epsilon greater than 0, there exists a positive integer capital N, such that for all n and m greater than or equal to capital N, the absolute value of xn minus xm is less than epsilon. The second definition tells us for every epsilon greater than 0, there exists a positive integer capital N, such that for all n greater than or equal to capital N, and for all positive integers k, the absolute value of xn plus k minus xn is less than epsilon. So we're going to prove that these two statements are equivalent. To do that, we're going to prove if 1 is true, then 2 is true. And then we're going to prove if 2 is true, then 1 is true. Let's start out by proving if 1 is true, then 2 is true. And so, to prove this, let's suppose 1 is true. From here, the whole goal is to prove that 2 holds. And we're trying to prove a statement about every epsilon greater than 0. So let's give ourselves an arbitrary epsilon greater than 0. From here, we want to find a positive integer capital N such that this is true. Now, since we know that 1 holds, this means we know that this first statement is true. And this first statement works for every positive real number. So in particular, it must work for the positive real number epsilon that we just introduced. So taking epsilon to be the epsilon we just introduced, we have that this is true. So there exists a positive integer capital N such that for all n and m greater than or equal to capital N, the absolute value of xn minus xm is less than epsilon. Now remember, the whole goal is to find a positive integer capital N such that this is true. And the claim is that if we take this positive integer to be the capital N we have in our proof, then this statement will be true. So taking capital N to be this capital N, let's prove that this statement is true. Well, since we're trying to prove a statement about every integer greater than or equal to capital N and every positive integer k, let's give ourselves an arbitrary integer greater than or equal to capital N and an arbitrary positive integer. I'll call them n and k. And from here, we want to show that this inequality is true. Now remember, we know that this statement is true. And this statement works for any 2 integers greater than or equal to capital N. So in particular, we're going to take n to be the n we have here, and we're going to take m to be n plus k, right? Certainly n and n plus k are greater than or equal to capital N. And so with these two choices, it follows that the absolute value of xn minus xn plus k is less than epsilon. And when it comes to absolute values, it's perfectly fine if we swap these two guys around. And so we have shown that this inequality is true. So we have proven this entire statement. And so this proves that 2 holds. So we have proven if 1 is true, then 2 is true. Now we're going to prove if 2 is true, then 1 is true. To prove that, suppose 2 is true. The whole goal from here is to prove that 1 holds. Well, since we're trying to prove a statement about every epsilon greater than 0, let's give ourselves an arbitrary epsilon greater than 0. From here, we want to find a positive integer capital N such that this is true. Now, since we know that 2 holds, this means we are given that this second statement is true. And this second statement works for every positive real number. So in particular, it must work for the epsilon that we have in our proof. So taking epsilon to be the epsilon we have in our proof, we have that this statement is true. So there exists a positive integer capital N such that for all n greater than or equal to capital N and for all positive integers k, the absolute value of xn plus k minus xn is less than epsilon. Now remember, the whole goal has been to find a positive integer such that this is true. And the claim is that if we take this positive integer to be capital N that we have in our proof, then this statement will be true. So, taking this positive integer to be capital N, we proceed to prove that this statement is true. And since we're trying to prove a statement about every two integers greater than or equal to capital N, let's give ourselves two arbitrary integers greater than or equal to capital N. I'll call them N and N. From here, the whole goal is to show that this inequality is true. And to show that this inequality is true, we're going to consider three cases. Either N is equal to M, N is greater than M, or N is less than M. Let's start with the case N is equal to M. In the case N is equal to M, well, let's write out the left-hand side of this inequality. We know N is equal to M, so we could replace M here with N. And this is just equal to 0. And 0 is clearly less than epsilon. So we have shown that the absolute value of xn minus xm is less than epsilon. So this completes case 1. Now let's move on to case 2 and consider n greater than n. Now, in this case, we want to somehow apply this statement in order to show that absolute value of xn minus xm is less than epsilon. Now, what we can do is we can take n in this statement to be m and k to be n minus m. Right? We know m is greater than or equal to n. That's what we have here. And we know that n minus m is a positive integer since n is greater than m. So with these two substitutions, this essentially becomes this. Right? We've substituted n for m and k for n minus m. We substituted n for m. We get that this inequality is true. But m plus n minus m is just equal to n. So we have absolute value of xn minus xm is less than epsilon. And so this completes case 2. Now let's move on to case 3, where n is less than n. And again, we're going to apply the statement to show that this inequality is true. In this case, we're going to take n to be n, and we're going to take k to be n minus n. These are valid choices since we know n is greater than or equal to capital N. That's what we have here. And n minus n is certainly a positive integer because m is greater than n. So with these two substitutions, this becomes this. So we've substituted n for n, and k for n minus n for n. So we have that this inequality is true. But then we know that this simplifies down to n, so we get this, but then let's remind ourselves it doesn't matter the order of these two terms. It's the same thing if we swap them around. And so we have shown that this inequality is true. So in all three cases, we have shown that this inequality is true. So given any two integers greater than or equal to capital N, this inequality is true. So we've proven that 1 holds. And so we have shown if 2 holds, then 1 holds. And so we have proven both directions. And so this completes the proof. We have proven that the two definitions of a Cauchy sequence are equivalent. And so yeah, that's pretty much it for this video.